started. Recording. I feel like there's less people here than normal. Is there some sort of like test or something going on?
They're all celebrating American Thanksgiving.
That is true, though I think that traditionally we don't have too many American students. It's not to say that it would, we don't have any, but I just don't think there's usually a lot. But maybe that's what it is.
No, that's fair. There's usually a lot of American students.
Oh, I didn't share the right thing. Share. But yeah, American Thanksgiving would totally be a valid excuse. Exactly. Clearly, Brandon knows what's up.
I agree. I would rather do counting and probability questions over eating turkey any day.
That's right. And spending time with family. And who do want to do that? I guess it depends on your family, right? But
that is very true.
There you go. Math's way better than turkey.
I think turkeys are underrated, but I'll still agree math is great.
Yeah, well, Brandon, so you should get your guests to help with the cleanup. I guess it depends on how well you know them. Hopefully they offered to help anyway, you would hope.
Okay, that's nice of them.
Mm-hmm. Yes, we're rolling 2 dice. We're rolling 2 6-sided dice. A is the sum of them is 7. B is the sum, or is one of the dice is odd, mutually exclusive, independent. There's 4 options. What are they? Yeah, this is one of the ones, if you really want, you can write these down, right? Like you roll 2 dice and you write them as 3, 4 is the first dice is a 3, the second dice is a 4. I actually think this is the sort of thing that might be a little bit easier to do with a table. I'm going to use a table. You don't have to use a table, but I think it's a little bit nicer to see if you use a table. Okay, so we're at 2/3. Let's do 30 more seconds and then we'll shut her down. All right, the correct answer is kind of like squeaking in there, squeaked ahead a little bit. All right, let's take a look at this. All right, so we're pretty well split. There's a slight plurality in D. D is the correct answer for the record, but lots of people said C and A, and a couple of people said B as well. So yeah, they are neither independent nor mutually exclusive. Okay, now mutually exclusive, I think, isn't too bad to see. Like I said, I'm going to actually kind of use a table to do this, but if you wanted to, you could write it out as pairs. So let me, stupid Zoom thing, go away. Okay, so I'm going to bring my table up. Okay, so I made this nice little table here, and this table is, let's say across the top is the dice rolls of the first die. Okay, so let's say that this is the first die right here, and then this is the second one on the left-hand side here. Okay, and my table here represents their sum. So we've got these two events, right? Maybe let me just write this on the side here. We've got E is equal to, or no, we said A. So A is that the sum is 7. And B is that one of the dice is odd. Dice is odd. Okay, so we can just, actually, you know what? Maybe let me color code these as well. So let's find where the sum is 7. So I'm going to look into my table and I'm going to like, oh, there's a 7, there's a 7, there's a 7, there's a 7. And it's this nice like anti-diagonal, right? And again, we could write that out. It's 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, et cetera, right? So we could write that out if we really, really wanted to. But again, I think that the table is quite nice. Okay, and let's maybe draw one of the dice is odd in blue. Okay, so we're going to get all of these, right? Because this is where the second dice is odd. This is where all right. And now let's do the first die is also odd. We get this, we get this, and we get this. Okay. So if they're mutually exclusive, we're saying there's no overlap whatsoever, right? So the sum doesn't need to be odd, it's just the dice. Well, A is the sum of 7, right? Like period. That event exists in and of itself. It doesn't see the event B at all. So the sum is just equal to 7. Oh, you read it as the sum is even? Nice, I like it. Odd plus or is it equal? So A is dependent on B, right? Yeah, exactly. Or actually here, let's put it another way. So let's do the mutually exclusive question first, because I think that's the easier one to answer. If these are mutually exclusive, there's no overlap, right? So mutually exclusive means no overlap, right? But I think we agree these definitely overlap, right? But these overlap. So we definitely are not mutually exclusive. Mutually exclusive. Okay. So now what we have to do is we have to figure out whether these events are independent. And the reason why we asked this specific question is because it is, so look at where the stuff that's blue and look at the stuff that's yellow. And there's definitely yellow stuff in the blue stuff, right? Like they overlap in exactly, I'll try and use another color. They overlap in the yellow, right? Like every yellow circle is part of the blue. Right? Okay, cool. Could you also say if they can't happen at the same time? I think that's a tricky thing. I wouldn't necessarily go down that route, but are you trying to like determine independence? Is that your objective there? Oh, for mutually exclusive. Sure. Yeah. Yeah, mutually exclusive means they can't both happen at the same time. Sure, that's a fine way of saying that. Yeah. Okay. Now, remember, two events are independent if the outcome of one does not affect the outcome of the other, right? So independent means one event does not affect the other. But here's the thing. If I claim that if I tell you you rolled a 7 I guarantee that that affects whether or not one of your dice was odd. Why? In fact, what's the probability that one of your dice is odd? Does anyone know? What is the probability that one of your dice is odd? Okay, so Brandon, right. In this case, if you roll a 7, there is a guarantee that one of your dice is odd. Does everyone agree? Like, look at where the 7s occur. Every single 7 is in a blue thing, right? Oh, I can't. So is that for the probability that a dice is odd? So it has to be a fraction though, right? Like, tell me, like, what is the fraction? But you were right. So what we see, let me maybe kind of write out what we know so far. These are not independent, since you definitely, if you sum to 7, one of your dice is for sure odd, right? And so rolling a set or summing to 7 definitely affects the other event. These are not independent, since if you sum to 7, 100% one of the dice, maybe that's a weird way of saying it. There is a 100% chance one die is odd, right? Now, the other way that we can check this, and here's how you actually check independence. Okay, so how do we know it's 100%? Okay, so let's look at it. So if it's this 7, okay, let's look at this 7 down here. That's a 1-6, right? One of the dice is odd. If we look at this one, that's a 2-5. One of the dice is odd. 3-4, 4-3, 5-2, 6-1. In every single one of those cases, one of the dice is odd, right? So there are examples where they are not mutually exclusive, but one is needed for the other, because here they have to go together. So some example. So this is an interesting question. So you're asking not independent. Actually, sorry, direct messenger, I'm not certain what you're asking. So it sounds like you're asking not independent and not mutually exclusive, but this is an example of not mutually independent, not mutually exclusive and not independent. And you can certainly be independent and mutually exclusive. Maybe the more interesting case is where you are dependent and mutually exclusive, right? Where it's not necessary, where what's not necessary. I mean, this is a very special case because it's 100%, but I mean, you can certainly be dependent without being 100%, right? Like, let's say I did the following experiment. I rolled a dice, and then based off of that, I flip that number of coins, right? So if I roll a 4, then I'm going to flip 4 coins. And I ask, let an event be that you rolled 2, or that you flip 2 heads. That definitely depends on the outcome of the dice, right? So the dice and, flipping 2 heads there is definitely dependent, even though it's not a guarantee that I would flip 2 heads sort of thing, right? Okay, cool. Okay, so the question is, what is the question asking again? If what is mutually exclusive? So it's asking if A and B are mutually exclusive, right? I.e., do A and B have any intersection? And they definitely do. They overlap in exactly A, right? So A is actually a subset of B. So if we're looking for the sum of 8, would it be independent? That's actually a really interesting question. And we can try and answer that in a second. So I really do like that question, but let's give it a second. So we'll be able to answer that question in a second, Owen, if you let me kind of show this part. So right now we're really depending on intuition, right, to tell us whether events are independent or not. And the goal is that we don't want to be able to do this. We'd like a mathematical way of determining if 2 events are independent, right? I think that's fair, because then you don't have to worry about language issues. You don't have to worry about, your interpretation. You can just depend on the computation, right? So that's kind of what we want. Now, 2 events are independent. If and only if the probability of their intersection is equal to the probability of E times the probability of F. Okay, so this is a check. This is the mathematical check for how you determine whether two events are independent. You compute the probability of their intersection, and if that's equal to the product of the probabilities, then that means that those two events are independent. Okay, so that's how we actually do it. Now, in this case, let's take a look at our events A and B. What is the probability of A? Okay, what is the yellow? What is the probability of the yellow? One in six, right? Or 6 out of 36, but yeah, exactly, 1 in 6. So in our case, so we've got the probability of A is 1 in 6. Okay, the probability of B is what? Let me go back up here. What's the probability of B? Okay, sure, yeah, 27 over 36, or 3/4, right? If we divide both those numbers by 9, we get 3/4, but Emin, you're absolutely correct, right? So we get 3/4. Okay, so the probability of A times the probability of B is going to be 1/6 times 3/4, and that's 1/8, right? 3/24, or if you want, you can, cancel out a 3 and a 6. Now, what is the probability of A intersect B? Okay, I'm going to go back up here and find for me all the things where A and B intersect. So the things that are both yellow and blue. Okay, what is the probability of A intersect B? Right, it's 1 in 6 again, right? It's equal to A. A is a subset of B, right? So it's 1/6. These are not equal, right? Right, so these events are not independent. Okay, or alternatively, they are dependent. Okay, now Owen asks a great question, which is, well, what if the sum is 8? Like, is there something special about the sum of 7? Well, let's find out. Okay, so here's just a different question, and again, you're really going to have to bank on the video for this. So the question was, if the sum is 8, does it change the answer? So let's just really quickly answer that question. And let's find where the sum is equal to 8. So here's an 8, here's an 8. Conveniently, these all kind of happen on the same row, right? The question was, why would it be 6 over 27? Why is what 6 over, what? Why wouldn't what be 6 over 27? The intersection? It would be 6 over 36. There's 36 outcomes, right? So Group, I think you're actually starting to do conditional probability. Yeah, exactly, which is actually conditional probability. So you're actually getting a little bit ahead of yourself. So what you were doing is a valid thing, but is not what we're doing here. But yeah, you're just getting a little ahead of yourself, right? Which is cool, which is super cool, right? Okay, so the probability of B is still the same. You know what? Maybe let me use a different color for this just to indicate like this isn't the yellow thing that I drew up there. So okay, so we're going to call this C, and that's the sum is 8, right? Okay, what is the probability of C? 5 and 36, right? There's 5 things which add up to 8 of our 36 total. So our probability is 5 out of 36. So the probability of C is 5 over 36, right? So that means that the probability, and again, we're looking at B and C, right? So the probability of B times the probability of C is 3/4 times 5 over 36, which is what, 5/48, right? I don't think it simplifies much more than that. 5 is prime, so unless I can divide 48 by 5, there's nothing I can do. And now let's determine what the probability of B intersects C is. Okay, so I'm going to go back up here. What is the probability of B intersects C? 1/18th, right? Or yeah, 2/36, right? Does everyone agree? Because there's only 2 things that are both green and blue, right? It is 5-3 and 3-5. Those are the only two possibilities of where you add up to 8 and one of your numbers is odd. So we get 1/18. Right? And again, these are not equal. So these events not independent. Therefore, not independent. So Owen, does that help? Why is it 1/18? Sure. So you're looking for the intersection, right? A intersect B. And what are the things that are both green and blue? Only these two things are green and blue. Yeah, 236. Yeah. Okay, and that's why it's 2, because those are the only two things. Okay, perfect. Okay, everyone's fine. Everyone understands what's going on. Everyone's okay. So it's nice, right, that you have this like computational way of actually determining independence. Okay, so what I'm actually going to do, and just let me do this now. I actually want to reuse this table for the next question. So I'm going to delete these things. Remember, this is all recorded, right? So it's not like this is gone forever. But I do actually want this table for the next question. So I'm going to, and hopefully copy it. Is that, yeah, that's copy. Okay. And so the next question is going to be similar. So I do want to paste it in just so that I have it. You guys all get to watch me do that. Okay, let's go to the next question now. Which is very similar, but is not the same. Okay, notice the difference, right? The bolded part is different than the previous question. No, you can label whichever one, right? The tables are totally symmetric. Sure. So, so for direct messenger, I can't show it right now because we're on this question, but go back and count the number of blue things that I had circled, right? Or if you have your own table, count the blue things and tell me how many there are. Or alternatively, here's maybe a better way. How many dice rolls are there where both dice are even? So how many options do you have for the first die? Right. No problem. Note though, again, this is kind of an interesting thing. Like, let's say, you know, the question was too big and you couldn't draw that table, right? And actually count 27. So the way to go about this is, you know, the problem with trying to compute how many things are where they're both even is that you can overcount, right? Because you want to say, oh, or sorry, where one of them is odd. Restart. Let's say you want to compute the number of ways that one of them is odd, right? Well, you say there's 18 ways for the first number to, you know, be odd, and there's 18 ways for the second way to be odd. But the problem is that you've overcounted, because certainly the answer is not 36, right? So the reason you've overcounted is you counted where both numbers are odd twice, right? So you then have to subtract that. So this is one of these examples where it's actually easier to, again, compute the complement. And the complement is, well, what if none of the numbers are odd? So in particular, what if they're both even? And the number of ways that both the dice can be even is precisely 9, because you have 3 options for the first one, 2, 4, or 6. You've got 3 options for the third one, 2, 4, or 6. That gives you 9 options, and 36 minus 9 is 27. Agam, yeah, so in this question, it doesn't tell you anything about the second die, so the second die can be whatever it wants. Which trick with the probabilities? The complement trick? Oh, for determining independence, you mean? Yeah, yeah, it's very good. Yeah, it's a very nice little trick. I mean, in some ways, it's the definition. It's not a trick, right? But yeah, it's definitely nice to have a computational way of being able to say, are these two events independent? Okay, we're at 2/3 have answered. Let's do another 30 seconds. Yeah, the previous answer was neither mutually exclusive nor independent. And being not independent is the same as being dependent, right? Right, exactly. It can't be mutually exclusive if they intersect. All right, so many of you have fallen for my trap. The answer is absolutely not D this time, right? This is a different question. The previous question said one of the die has to be odd. This one says only the first die has to be odd, okay? So I will tell you that the answer is not A or not D, but let's figure out what the correct answer is minus the Freudian slip. So we've got the same sort of question. And this time again, we have, let's say A is the sum is 7. Oh, see, I wrote even. And then B is the first die is odd. Okay, so I'm going to go through same thing that we did before, right? Here's the 7s. Okay, and then the first die is odd. Is that, right? Okay, are these mutually exclusive? No, right? There's an overlap for sure, right? So they're not mutually exclusive. Okay, now the question is, are they independent? Right? So let's do it. Okay, let's not guess. And then I'll explain after you what the answer is. What is the probability of A? It's the same as it's always been. It's 1/6, right? What's the probability of B? Right, a half. So the probability of A times the probability of B is equal to 1/12, right? Everyone agrees? Now, what is the probability of the intersection? Yeah, Namir, was that an answer for what I just asked? Yeah, exactly. And Brandon, yeah, 3/36. You're both absolutely right. Yep, these are equal. So these events are independent. The correct answer is A. Okay. Okay, yeah. So a couple of people are asking, why is the probability of B a half? So again, count the blue. How many things are circled in blue? There's a couple of answers to this, but let's do the easy way first. So yeah, there's 8, maybe 8. I don't know what you're saying. Yeah. Right, but exactly. Namir has pointed out there's 18 things circled in blue. So that actually means that there are 18 divided by 36 is the probability. So that gives a half, right? Exactly. Yeah. The probability of it. Oh, so, yeah, you're right. 1/12. Thank you. Thank you, Chen. Yep. Okay. So, but here's another way of thinking about it. Even though the sum or the roll of the first die is independent from the second die. Does everyone agree? Like whatever you roll in the first die does not affect what you get on the second die, right? Those are independent. So the probability that your first die is odd is just the probability that your first die is odd, right? Like you don't care about the second dice. Whatever the second dice rolls doesn't affect the first dice. So what's the probability that when you roll six-sided dice that the face is odd? It's 50-50, right? Because there's 3 odd faces and there's 3 even faces, right? Right. Okay, sure. Cool. I'm glad that it makes sense though. Oh, I see what you're saying. Yeah. I see. You're asking not about the 1/2 on the P of B, but the 1/12 because I screwed that up. Okay, so is everyone okay with this? Now, do you understand intuitively why these events are independent? Right? So even if we didn't do the mathematics and I asked you to tell me that these 2 events are independent, I claim that if you think about this question correctly, you can understand that these events are independent without doing any mathematics. How do we do this if we had an odd face die? So if we assume that such a thing exists, I mean, you still just do the same thing, right? So this is a direct message question. So if we had an odd face die, how would you do it? You do the exact same thing. Just write out your table if you really wanted to, or again, do it algebraically and just write out the pairs, the tuples, and do the exact same thing, right? And compute this table and see what you get. Right, okay, so how do you know without math? So notice that let's say that I rolled an even dice, or my first die is, sorry, let's say my first die is odd. How many ways are there if I roll an odd die is there to get a 7? Like basically how many of the 7s are in the blue things? There's 3, right? So if I roll a 1, a 7 is still possible. If I roll a 3, a 7 is still possible. And if I roll a 5, a 7 is still possible. Now, if my first die was even, how many ways are there to get a 7? Namely, how many exactly, right? There are 3 7s that aren't in the blue thing. So the point is that doesn't matter what your first die roll is, it's still possible to get a 7 with equal probability, regardless of whether your first die was even or your first die was odd. Does that make sense? So these events are independent because you can still always get a 7. Note that 7 is the only number for which this is true. Do you see that? 7 is the only number such that if you sum to 7, you have an equal number of things outside the blue and inside the blue, right? Every other number, and this would have been a dependent question. Because what occurs whenever you add 2 dice? Oh, sure, yeah, other than an 11, I guess. And therefore a 3 as well. Or I guess a 5. No, hold on. Something's wrong here because you should still... You're right. Okay, sorry. The answer here is not that the blue and the yellow are the same. It's that... Okay, let me try and explain this a different way. That is more or less how I explain the 7, but you're right. When we want to do the 5, because you'd say, hey, listen, if I look at the 5s, there are 2 inside the blue and then there's 2 outside the blue. But the problem is that what if I rolled and Jack, this goes to your thing about 11 and 3 and 5. If the first die is a 5, it is impossible for me to sum to 5. Do you agree? And 9, yeah, sure. Same thing with the 9 down. Yeah, absolutely. If the first die is a 9, well, the first die can't be a 9, but if the first die is like 1, if the first die is a 1, it's impossible to roll a 9 or to sum to 9. Do you agree? So that actually does affect the outcome, right? Those events are still dependent, even though there isn't the same number of things inside and outside, right? So like what I'm saying here is if we look at the 9s, sure, there are 2 9s outside and there are 2 9s inside, but the point is that there's no 9s in here. And that actually screws everything up. And again, if you're not certain why that's true, you can just compute the probability. Or again, if the first die is a 1, you're screwed. There's no way you can sum to a 9. Yeah. So it has to be every blue circle and also have equal numbers inside and out. It's more complicated than that. It is. I would say trust the math. It's not like the sort of thing where we can metagame what this particular chart looks like. And more importantly, even if we did come up with a rule for this chart, the moment I give you different sided dice, that rule breaks. So we shouldn't worry about that. What we want to do is say, let's look at the mathematics. And Namir, yeah, exactly, 100%. No matter what the first die is, you can always still get a 7. Right? Does everyone see that? No matter what the first roll is, it's always still possible to get a 7. And in fact, you have an equal likelihood of getting a 7, regardless of whether you rolled an even number first or an odd number first. You can always get a 7, but you can't always get an 11, right? If the first die is not a 5 or a 6, you're screwed. There's no chance you can get an 11. So that ends up affects the independence. And Evan, sorry, I missed your statement, but hopefully Aziz got it. And Christian, exactly. Yeah, that's the rule. Okay, that is in effect, even though it's not necessarily how I defined it in this course, that is actually the definition of independence. Okay, that the probability of A intersect B is precisely the probability of A times the probability of B. So if we wanted to do this with 3 dice, how would that work? Would we use the same process? Well, it's a little bit harder to do it exactly this way, because if you want to write out the sum of 3 dice, it's a little bit more complicated. You'd get like this 3-dimensional 6 by 6 by 6 cube. So you probably wouldn't necessarily want to do it that way. But you would do something similar where you'd actually write it out. So for example, in this case, what I could do if I wasn't using the table is I could just write out all of the 18 things, right? Or actually what I would do is I'd say, let's find the probability. I know what the probability of B is, and I know what the probability of A is, because like I said, probability of B is a half because the first die is independent from the second. And the probability of A, you could just count because there's only so many 7s. And then I would say, well, what is A intersect B? Okay, so without looking at our chart here, what is A intersect B? So you have to sum to 7, and the first die has to be odd, right? Okay, so what are your options? 1, 6, 3, 4, and 5, 2. Right, do you agree? And so I'm done, right? Like I know I can now compute the probability of A intersect B. I can compute the probability of A. I can compute the probability of B. And I didn't have to draw a table. I just knew what these probabilities were because I can count. So I'm sure, and here's an important lesson, everyone. I've shown you this table because I think it's nice to be able to illustrate this. But the whole reason that we taught you how to count was so that you didn't have to draw the table. Does that make sense? So that if we get at this thing where I say roll 3 die and do the same sort of thing, you can count how many events occur and therefore determine the probability without having to draw this monstrous 6 by 6 by 6 table, right? Which is really big, right? That has like what's 6 times 6 times 6, 36 times 6, so 216, right? Like that's a big table, right? You don't want to draw that table out. So that's why we taught you how to count. It's just in this case, I want to be able to illustrate it. So I did give you that table. Okay. But actually, this leads into a great question. What if we rolled 3 dice? Okay, well, let's roll 3 dice. Yeah, Brandon, this is an important question, right? Like, should you do this via the complement or not? Well, first of all, yeah, exactly. I mean, one, you can meta it and look at the answers. Is it possible? So I've got this question. Is it possible to draw a table for 3 dice? The answer is yes, but you either need to be really complicated in how you draw it, or it needs to be 3-dimensional. And obviously this isn't going to generalize well beyond 3, right? So if I give you 4 dice, you're probably not going to draw a 4-dimensional table, right? So the answer is no. This kind of like is nice when you have 2 dice, but beyond that, you kind of have to do the algebraic approach, which is what I just kind of drew, where you say A intersect B equals, and you don't draw the table, but you actually just enumerate all the possible pairs that you're interested in. And we're going to do the same thing here, right? Don't try and draw a table for this. I don't think it's reasonable. And we'll do it that way. Yeah, but what about 5, Connie? Okay, I'm going to give you 30 seconds to get your answers in. That's okay, Theodora, as long as you know what the right one is. Kurdi. But in the intersection, both don't count. Well, I don't necessarily know why you're talking about the intersection, but those are different. You actually count those as being different things. Like, it's true they add to the same thing, but they are different because you assume that you can distinguish your die, right? You know which die was the first die, which die was the second die, and so on. No problem. Okay, so let's take a look. The class is split between C and D, with one more person choosing D. And maybe that was you, Teodoro, which maybe threw off the balance. The correct answer is C, though. Okay, so C is the correct answer. It's 1 minus 10 over 6 cubed. And again, you can see even just by the presentation, now obviously you wouldn't have this benefit in a term test, but here we definitely want to do the complement. And the reason for this is let's just think about let's just think about how many ways, if you roll 3 die, what's the smallest number that you can get? Right, exactly. And Jack, that's a 1, 1, 1. So 3 is the smallest number you can get. What's the biggest number you can get? Ah, okay. Careful, Lubna, right? Because 6 plus 6 plus 6. Okay, hold on, everyone. 6 plus 6 plus 6. Maybe you meant 3 times 6, Lubna, right? Like, right? Because that would be the correct answer. So 6 plus 6 plus 6 is 18, right? In fact, if any of you have ever played Dungeons and Dragons, you know that traditionally you can only your ability scores can only go between 3 and 18. And the reason for that is precisely because to do it, you would traditionally roll 3d6, right? Exactly, right? So the hint here is to find the complement. But even if we just looked at the number of possible outcomes and you said, look, the outcomes can be any of these 3 numbers, 3, 4, 5, 6, 7, dot, 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 all the way to 18. And we said, listen, the number has to be at least 6. Would you rather compute this or would you rather compute this? Do you know what I'm saying? Like exactly, totally 3, 4, 5 is got to be easier. And in fact, when you think about it, you're like, there really aren't that many ways to roll a 3. And so there really aren't that many ways to roll a 4 either. Like the thing where I compute 3, 4, 5 seems totally reasonable. Whereas 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 seems like that could be a lot of work, right? So we want to compute the complement. So let's compute, or let's say let E, did we name it? No, we didn't. E equals the sum is at least 16, or 6, is at least 6. So what we're after is the complement, right? So EC is the sum is at most 5. Okay, so let's just go through it. How many ways can we sum to a 3? One, and it's 1, 1, 1, right? Okay, sum to 4. How many ways? And write them all out if you want. Yeah, exactly. There's 3 ways. And if we want to, let me just write them out. But Namir, you're absolutely correct. Let me just write them all out for anyone who's not certain, right? And then sum to 5. Yeah, there's 6 ways. Exactly. Yeah, Sylvia, you're just on the ball there, like super, super quick, right? So we got 2, 2, 1. And so in practice, everybody, here's how I'd actually do it. I wouldn't write out all 6 ways. What I'd say is 2, 2, 1 is an option. And then there are 3 of those, right? Depending on what are all the possible arrangements of this thing. Well, it's 3 factorial divided by 2 factorial. Do you agree? It's how many ways are there arranging 2, 2, 1? Well, by our formula, there's 3 factorial ways of doing that, but one of those numbers is repeated twice. So that gives me 3 factorial divided by 2 factorial, right? So there's 3 ways of doing that. And same thing with 1, 1, 3, right? So there's 3 ways of doing that. Does everyone see that? How you can make your life a little bit easier, again, by using counting arguments? So you can list them all out. In this case, it's not too bad, but again, use your counting arguments. If you have them, you can just make your life a little bit easier, right? Or equivalently, there's 3 choose 1 ways because you're going to choose where to put the 1, and then the other 2 numbers have to be the 2. Okay, so in total here, therefore, there are 10 possible ways that we sum to at most 5, right? Because there are 1 option for 3, 3 for 4, 6 for 5. So the probability of the complement of E is going to be 10 over, what's the total number of ways? I mean, the solution gave it away. 6 and 3, exactly. Thus, the probability of E is 1 minus that, right? And this was C. Okay, makes sense? Any questions? Why 6 to 3? Okay, how many options for the first die? So we roll 3 dice. How many options for this one? Right, 6-sided. Right. Okay, cool. Anyone else? Any questions? What 6 times it's 6 to the power of the number of die, right? We want to be careful there. It's not times the number, because in this case it would be 6. That would be 6 times 3, right? Which would only be 18, but in this case, it's actually 6 to the power 3, which is 216. Yeah. Yeah. So it's 6 to the power 3. Yeah. 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 So it's the number of possible, like if you roll NDKs, right? NDK, that means you've got N boxes. And then each box, there's K options. Right? So the option will be K. The number of ways will be K to the power of N. Because it'd be K times K times K times K N times. Good? Everyone's happy. Any questions? Okay. In that case, then we'll go to office hours. Give me about just, again, 5 minutes here, refill my water, all those sorts of things. Aziz, are you hanging around for a little bit?
I'll hang out till you come back, then I'm heading on. So I'll
Okay.
hang out 5 minutes here, going to grab some more.
Yeah, sounds good. Okay, so give me 5 minutes. I'll be back. Otherwise, that finishes the lecture. So for those of you who are taking off, have a good weekend. I'll see you next week. Otherwise, I'll be right back.
I mean, I'm going to be here for the next 5 minutes. So if you guys have any questions, feel free to either type them up in the chat or just ask. That's a good question. Getting a bunch of private questions here, so I'm going to answer them as they come in order. How can we apply counting? Okay, how can we apply counting formula to for the sum to 5? So I'm not sure what you mean. So I got a question saying, how can we apply the counting formula for the sum to 5? Oh, like what we were just doing right now, like earlier for this question. Okay, so for that one, it's a bit trickier. So like you need to kind of do them in terms of cases, like we just did right now. There's no way where you can get the probability of the complement without cases. So you're gonna have to get the cases where like the 3 ones are repeating, and then when the ones are repeating twice, and then when the ones are repeat like only happening once, and you can do them like separately, and you can combine them. But in these cases, sometimes it's better just to add them up rather than actually physically do them all at once, because I feel like that makes them a little more complicated here. I got another question. I don't think I'm not doing any more marking for this semester. I'm going to mark again next semester, but I do all the regrades. And for the people that emailed me for the regrades, I'm really backed up on them right now, but I'm kind of working on them. You should get your regrade marks if you submitted one by this weekend. So look out for that if you sent it. I see some talk about some accounting tests tomorrow, so good luck with that for whoever's doing that as well. That's great. I don't know if I'm missing any questions here. For some, oh, I got a few assignment questions here. First assignment 6 question. No, so there's a question about assignment 6 about specifically the straights. So the ace is a special card where ace can be the last number in the sequence or the first number. So you know how, like for example, like I don't know if any of you guys have played a deck of cards. Ace a lot of times can act as like a beginning and an end at the same time. So usually after the king, there's an ace, and before the 2, there's an ace. So when you're doing a straight, you can have a 10, jack, queen, king, ace straight. So like from 10 to ace, because ace is considered the last card. But you can also have ace as the beginning of your straight. So ace, 2, 3, 4, 5. So that is a possible straight as well. You cannot have an ace anywhere as a filler for a straight. You cannot have, for example, like 4, 5, 6, 7, 8 ace. That's not a straight. Ace only acts as the last card and the first one. It can act as either, but it doesn't connect both of them together. So another thing that cannot happen is you can't have like Jack, Queen, King, Ace 2. Like ace does not connect both sides of the circle. It's not like a circle. It's just you can think of ace as the last card and it could be the first card. It's interchanged to both. So ace, ace 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, ace will like you have to think about ace as like, although it's only one card, it can actually start the deck or end it. So in case of straight specifically, you can have the ace at the beginning, where you can do like in a straight, you can do ace 2, 3, 4, 5 as a straight, or ace 2, 3, 4, sorry, specifically as a straight. Or you can have the ace at the end of your deck, so after the king. So you know how it goes usually 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. You can have the ace at the end, so you can have the straight at the end as well. So you have to be careful that ace can be at the beginning and at the end, but it does not connect both the circle together. So you can't start at the end and have like a Queen, King, Ace, and then go 2, 3, and that's a straight. So can you have, no, you cannot have, so I have an example here. Can you have 3, 4, 5, 6, 7, 8 ace? No, definitely not. Ace is only the last number of like, so if you have to write them all down, you write the 2 to king down, like 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. And ace can work at the beginning of this or at the end of this. But it does not like work as a loop where you have to kind of continue the straight from beginning to end. And you can't just plug in the ace anywhere you want in the middle and continue straight. Right? So like you can't just, yeah, Tyler's writing them down right now, as you can see. But like you can't plug in the ace between the 6 and the 7 and say that's where I'm going to finish off my straight. Right? So yeah, it's exactly what Tyler just drew, right? The ace can be plugged in either place to continue the straight, but it does not loop the whole thing around. That's the key. You can't just take the Queen, King, Ace, and then go back to 2, 3, 4 and say now I have a straight. That's not how it works.
Yeah, it's just this one weird rule. I mean, aces usually are both high and low. It's one of the things that make, you know, a deck of cards interesting. Yeah, aces are weird cards because they can be both high and low. But yeah, that's it. They're either the high card or they're the low card. As he says, they don't close a circle. That's not true, but they can. They're two-faced, right? Like sometimes they're the low card, sometimes they're the high card, depending on what's convenient for you. You just treat them however you like.
Yeah, and I got a few direct messages about the professor card. The professor card shouldn't change things because the professor card just slots in after the king. It really doesn't change things. It just means that now instead of the ace coming after the king and before the 2, it comes after the professor and before the 2. But it doesn't change the thing in terms of the loop and how things are. It's just adding an extra number. Yeah, 1 or 11, not 1 or 10.
Yeah, ace is an 11 in blackjack. Which again, I guess is weird, right? Like,
yeah. So I would like, yeah. So ace is just kind of this filler where you can either put it at the end, and if you put it at the end, then it like in that case like Jack, Queen, King, I guess Professor Ace is like a straight, or you can put it at the beginning where Ace 2, 3, 4, 5, 6, 7 is the straight, or up to 6, I think, not 7, but same point.
Okay, hold on. Yeah, there's a couple of things here. Where 2 is the highest rank, it's present if anyone. Sure, I think like a bunch of us have probably played a version of that game, one form or another. Can't you choose in blackjack? Yes, yeah, you can choose whether it's an ace or 11, but your choice is almost pretty much always forced, right? In that you'll always choose the biggest hand you can that doesn't bust. So in blackjack, your choice is always evident. It's not like that you actually get to choose, right? Like if you have a king, ace, ace, you have 12. You don't have, 32 because that would be a bust.
30.
Yeah, right. Because ace would be 11 and then a 10. Yeah. So like you would always choose the aces in a way that maximizes your hand, but doesn't cause you to bust.
In blackjack, if you ever have an ace king, that means you did something wrong. You should never have an ace king in your hand.
Yes, yeah, that should actually be impossible. Well, I guess it's not impossible. You could have 2 aces, decided not to have split for whatever
there's
reason.
No reason. There's no way you don't split aces at blackjack.
Yeah, you totally split if you're dealt pair of aces.
Yeah, that's just No.
Because you're just asking for double blackjack, right?
Yeah, you're just asking for it, and if not, you're asking for a 12 to be dealt to you because you're probably going to get like a 10.
Exactly. And then you're going to hate yourself because that would have been a blackjack, right?
That would have been at least one blackjack. So
yes, Agam. Yeah, it is. Anyway, Aziz, if you got to run, take off.
Yeah, I'm probably gonna head out here.
Okay.
Explaining more blackjack to the students.
Yeah. lots of card questions, I'm sure. All right, man. See you later.
See you guys.
Theodora, yes, that is exactly right. Okay, so a couple of people have asked for something like the assignment question 1 and assignment question 2. So I guess we can do kind of both of these things like here. Okay, so I was specifically asked to talk about like full houses. And again, obviously I'm not going to do the question for you that's on the assignment, but we can talk about full houses, normal full houses, right? So full houses in a standard deck of 5 cards. And assignment 5 grades will be released? No idea. The TAs who have to mark that one are being really, really slow. So actually, I don't even think they've started, but they're also getting hit on midterms a lot. So hopefully I'm going to kick their butts and it'll be in the next couple days here. Let's see. So Kurdi, the difference between an over full house and a full house, I mean, you can't have an over full house in a 5-card game because it needs 7 cards, right? So full house is 3 of a kind followed by 2 of a kind, and over full house is 4 of a kind followed by 3 of a kind, right? Yeah, sure. Okay, so let's do a full house, right? So remember, a full house is 3 of a kind followed by 2 of a kind. So the way that we're going to do this for a full house, and again, there's kind of a couple of ways to do this, but they're all pretty similar. The way I would do it first is I would choose the ranks. Okay, so I've got 3 of a kind. Maybe let me draw them in different colors. So the 3 of a kind is going to be yellow. Okay, and then I'm going to choose another 2 cards to complement the full house. Now, how many options do I have for the rank of the 3 of a kind? Standard deck. 13, choose 1. 13, exactly. All those are the same thing. We've got 13 possible ranks. I can choose any of them. There's no restrictions whatsoever. So I have 13 options for the rank of this card. Okay. While we're here, let's finish it. Now that I've chosen the rank, let's say I chose like an 8 or something. How many ways are there to choose the suits for these? Exactly, 4, choose 3. Does everyone agree? Because there's 4 suits and I need to choose 3 of them. The order doesn't matter because they're all 8s. Okay. Why can't suits be 13, choose 3? So Kurdi, in that case, you're saying I have 13 ranks and I want to choose 3 of them. That's like saying I'm going to choose a 7, a 10, and a queen. But for this one, they all have to be 8, right? That's what I'm saying. Like they all have to be the same number, right? Oh, why can't suits? Sorry, why can't suits? Yeah, there's only 4 suits. So once, yeah, I read that as ranks, sorry. Once I've chosen, these are all going to be 8s. There's only 4 suits that I can choose from, right? Clubs, diamonds, spades, and hearts. So I need to decide, I don't know, Dodd, either tonight or probably tomorrow before noon. So I need to decide which of these 4 I'm going to assign to these 8. And maybe I'll do something like clubs, spades, and hearts like that. Okay, cool. So everyone's fine. Like that completely takes care of the 3 of a kind. Okay. So now how many ranks do I have for the blue, for the 2 of a kind? Exactly. I've got 12 options for this because I can't use the 8, right? Or I can't use whatever I chose for the 3 of a kind. So I have to use something different. So now I only have 12 exactly, and 4 choose 2 suits. 12 options for rank. And then there's 2 cards. And yeah, Doug, I already answered that. Did you just send it again by accident? I'll either do it tonight or like probably before noon tomorrow. And then 4 choose 2 for suits. Okay, so for anyone who's asking, is like, are there any part of that? So there was like 4 steps where we choose the rank for each and we choose the suits for each. Is anyone not certain about any of those facts? Like, why did we choose this number? Why is it this number? Could we have done this instead? Yeah, this is a 5-card hand. Yeah. Okay, let's do a similar one though, because there's another one that I want to do here that's related and important. Does everyone know what a 2-pair is? Right? 2 twos of a kind. 2 of a kind. Yeah, something like that. However we pluralize that, right? So basically what we're going to have is we're going to have a 2 of a kind, a different 2 of a kind, and then a fifth card, right? And yeah, exactly. You multiply everything. Thanks, Jack. Okay, so and notably, the blue and the white can't be the same as the yellow, right? These all three have to be different ranks. Does that make sense? Does everyone understand what we're trying to do here when I do a 2-pair? Okay, somebody tell me, what do you want to do first? Okay, let's do ranks. So how do I choose the ranks for this question? Okay, and Owen, I'm going to ignore you for now. Okay. So we're getting a lot of 13 for this, 12 for this, and 11 for this. Does everyone agree? That's not correct. Okay, Sean, for what? Because that's not the whole answer. What is your answer for? Not for yellow, because we don't want 2 different ranks, right? We want the yellows to all be the same. Gerber tap, yes, that's correct. Yeah, we're just doing a rank. Okay, Ariata, 13, choose 2 for the 2 pairs. And then how do I choose the last one? No. 11. 11, choose 1 or 11. So what is the difference here? No, there's nothing about ranks being adjacent. Why did I have to use, let me put it this way. Okay, Kurdi, you might have it because you took 2 numbers for the blue and the yellow. I did take 2 numbers for the blue and the yellow. But why did I use choose? Or equivalently, what I could have done here, same thing, I could have done 13 times 12 divided by 2. That's the same answer. Oh, and I'm not quite certain what you did there. 13 choose 2. What's the 3 choose 2? I don't quite know what the 3 choose 2 is. The rank for the blue and the yellow determine what white can be? No, it doesn't. Exactly, Ariana. Exactly. The pairs can interchange their order. Exactly. And Brandon, you said the same thing. The order of the pairs doesn't matter. Does everyone agree? So if I choose these to be 8s and these are 4s, and then this is a 7, that is not different than this. Right? Those are the same. Does everyone agree? I've got 2 pairs of 4s, 2 pairs of 8s, and a 7. Yeah, so we double overcounted. Or equivalently, we want to say the order doesn't matter. Note that that's not true in a full house. In a full house, the order does matter, right? Because the rank that I choose for the 3 of a kind is different than the rank that I choose for the 2 of a kind, right? If I chose 8s and 4s up here, that is actually different than a 3 4s and 2 8s, right? So up here, these are different, but down here, these are the same. Okay. So you can do it however you want. So you can do, as Ariana said, so we can do 13, choose 2 for these 2, right? So you're saying order doesn't matter. Right, there's no overcounting for the full house, right? Because order did matter there. There's 11 for this, and then you would do 4, choose 2, 4, choose 2, 4, choose 1, and multiply all those together and you get it. Sure, we can do 3 pair as well. So it was just saying 13, choose 3 times 3, choose 2 times 1, choose 1 equals 13, choose 2 times 11, choose 1. Oh, and I'm still not certain what you're saying. Why are you doing 3, choose 2? Oh, okay. So 13, choose 3 is you chose the ranks of all 3 cards. And then 3, choose 2, where you were assigning which ones were the 2 of a kind, which ones were the pairs. Yes, that's totally fine. So Owen has a slick second answer, which is to do 13, choose 2, 13, choose 3. So this is you choose all 3 ranks. Okay, and then multiply that by 3, choose 2. And this is where you're deciding which of them are the pairs, right? Which is the yellow and which is the blue. Right? And then times 1, choose 1. And yes, that does work out the same. Absolutely. Right, so that's kind of a nice, interesting example because there's really 2 totally different ways of doing this. Right, but they give you the same answer. Okay, and but for yeah, I mean, Gilbert, I can't confirm either way, but I would say that seems reasonable, right? Like that is not a like wildly incorrect thing. I can't say whether it's correct or incorrect, but I would say like I don't see anything obviously wrong with it. I was asked to do 3 pair. Okay, or not 3 pair. Actually, we don't want to. If we do 3 pair, we have to do a 6 card hand. So do we want to do a 6 card hand, or do we want 3 of a kind? Like which of these do we want? 6 cards. Okay. Okay, so let's do a 6 card hand. We're trying to do 3 pair. What do we do? So ranks first, right? Because suits, I think everyone knows how to do suits, right? Like we're not worried about suits at all. Suits are never tricky. Yeah, this is 3 2 pairs. Yeah. 13, choose 3. Beautiful. And we're done, right? That's it for ranks. 13, choose 3. And then you do suits. 4, choose 2, 4, choose 2, 4, choose 2. Sweet, no problem. Okay, so I was asked to do something like the assignment 2, part 2. Let me just take a look at it and remind myself what it says. Yeah, and exactly. So, and as Kurdi says, the one that's like 2 part 2 is very similar to poll question 15. And much to, I think, Brandon's chagrin, realize that the answers to that poll question give a huge hint as to what you're supposed to do. Right? Aiden, I'm not certain what you're asking. So sorry, if I said assignment 2, I meant assignment 6, question 2. Yeah. When do we do the 4, choose 2 3 times? Do we add them or multiply? Yeah, you multiply. Yeah, as Namira says. Yeah. 3, choose 2 where? Like this 3, choose 2? Connie, is that the one you wanted? Okay, so with the 13, choose 3. So using these suits above, what we're going to do is we're going to choose 8, 4, and 7. Okay, so we've just chosen the 3 ranks, but we haven't decided which of these ranks are the pairs and which one is the one that stands alone, right? So we need to decide which of these numbers is the yellow number, which is the blue number, and which is the white number. And the total number of ways that once we've chosen these 3 numbers, we can decide which are the pairs and which is the white number is precisely 3 choose 2, right? So we've got 3 options. We're going to choose 2 of them to be the pairs. And that's why it's 3 choose 2. Yeah, it's not for the suits. It's for assigning the ranks to the different parts of the hand. Yeah. So the or Kurdi, this is a great question. Okay, yeah, let me answer this quickly. So 3d6. So I think this is in the notes somewhere. 3d6 is 3 6-sided dice, right? So if we said 3d20, this would be roll 3 20-sided dice. So Connie, 2 pair is that you've got 2 of a kinds and then a different 5th card. Yeah, there's no restriction on suits. Obviously, you still have to take suits into consideration when you count them, but there's no restriction on suits. It doesn't say that the suits have to be a particular type. Okay. So this question is, how many hands include at least 1 professor and at least 1 smile, right? So again, like poll question 15 from last week, I'm just going to pull that up as well so I can see what it says. Because I think it was kings and hearts or something. Yeah, kings and hearts. Cool. So poll question 15 from last week. Okay. So it was, how many 3-card hands have at least 1 king and at least 1 heart? Okay. Nice. 11 was similar, but 11 is, I think, an or. Yeah, so 11 is an or statement, Owen, and then 15 is an and. So you're right, they're both very similar, but there is just this difference between the and the or, and is actually a little bit harder, right? Yeah, no problem. So let's let E be the hands that have at least 1 king. Let's let F be the hands with at least 1 heart. Okay, so we're asked to count E intersect F, right? That's what we want to know. We want to know how many things are in this set. Does everyone agree? Everyone's okay? Right? Okay. Now, I think that it's going to be easier to do this by counting the complement, right? Because when you say at least 1 hand, like at least 1 king, could be 1 king, 2 king, or 3 kings, right? But the complement of at least 1 king is just no kings, right? And that seems to me like it's probably going to be easier to count. So instead, let's count E intersect F complement. What is the complement of E intersect F? No kings or no hearts, exactly. Is everyone okay with that? Okay, everyone's good? Like, don't wait till I'm done the question to say, hey, I don't understand what's going on here, right? If something doesn't make sense, you should say something Kurdi, you could. I would write it out in words if you want, or even better, use like set builder and set operations like this. That would be probably pretty good too. Okay, I'm going to assume everyone's okay. Like if you don't say anything, I'm going to assume you're fine. But again, you really should say something if something doesn't make sense at this point, because now what we're going to do is we are going to compute the number of hands with no kings or no hearts. Okay. So how many, Brandon, I'm not certain. I did that once and I don't remember how to fix it. Like you have, there's a control somewhere. So I'm using, right, a surface. I don't know if you're using an iPad or something, but somewhere there has, like, I'm resting my hand on my thing right now and I'm even moving it around and it has like palm detection. So it knows when I'm writing and doesn't like turns off my hand. Yeah, I don't know. You'll have to look at your settings and see if it has like some sort of palm detection to detect whether or not, you know, you're writing on it, but it knows when I'm writing and then turns off the finger or, you know, the skin touching way of doing things. For doing that, maybe. And yeah, I think you're on the right path, but I think, yeah, something's worded a little bit incorrectly in your thing. So here, let's do this, because if I had had time last week, I would have done this question. So let's do this. How many ways are there of choosing a 3-card hand, 3 cards with no king? And Kurdi, exactly, there's 48 cards with no kings. So how many ways can I? Yeah, Connie, we'll get to that. We'll get to that. Okay, so there's 48, choose 3. Does everyone agree? 48, choose 3 ways of doing no kings whatsoever in a 3-card hand. Because we took our 52 cards, we took out the kings, right? There's 4 kings, we took them out, so that left 48 cards, and then we chose 3 of them. Everyone agrees? Everyone's happy? Okay. How many ways to do no hearts? And again, I feel like Kurdi, you typed it in and we're just waiting for me to say it, and then boom, you hit enter. Right? So 39, choose 3 ways of choosing no hearts. You take your 52 cards, you throw away your hearts, that leaves 39 left. There are 39, choose 3 ways of doing this, right? Gerber tab, exactly, yeah. But there's a problem here. What is the problem? There are repeats, there's overlap. In particular, what did we overlap? What did we count? Like if you had to describe it to me as you would when you're explaining. Okay, so yeah, it's true. Well, no, wait, what about the King of Hearts? The King of Hearts was never part of our computation. Or do you mean that the King of Hearts, yeah, where did the King of Hearts come in? There's no King of Hearts. Right, and Kurdi, that's exactly it. In our no kings hand, we also counted some of the hands that don't have any hearts. Do you agree? Right? Because for example, here is a no kings hand, 3 of clubs, 2 of spades, and the 10 of diamonds. Right? That is no kings, right? You agree? That hand has no kings, but it also has no hearts. So it got counted in both these hands. So I've counted this hand twice. It's not even, it's not the King of Hearts in this case, right? Because at no point did we ever include any hand with the King of Hearts, because the King of Hearts is it's true that the, what do I want to say here? Yes, it's okay. Yes, the King of Hearts is an example of something that has been removed twice, but I don't want to think about it as removing. So Agam, I think there's a sense in which what you're saying is correct, and I think a lot of people are saying this as well. I'm counting the number of hands with no kings or that have no hearts, and it's true, neither of those includes the King of Hearts. There is a sense in which I've removed those twice, but I'm not counting how many. I mean, I am counting how many things I've removed, but let's not worry about that yet. I'm just trying to figure out how many hands have no kings and how many hands have no hearts, right? And exactly, Namir, some hands have both no kings and no hearts, right? And that's exactly what you're saying. So all the hands that have no kings and no hearts were counted in both sets, right? So note, all hands with no kings and no hearts were counted twice. Okay, so in order to fix this, what I'm going to do is I have to remove, if I counted every hand that has no kings and no hearts twice, I need to remove that, like one set of those from what I've counted here, right? So how many hands have no kings and no hearts? Yeah, okay, that's how many cards, right? There are 36 cards with no kings and no, that are not a king and not a heart. Does everyone agree? Are not a king nor a heart. Exactly, and then that means that there are 36 choose 3 hands. There are 36 choose 3 hands with no king and no heart. So what do we have? We had 48 choose 3 plus 39 choose 3 minus 36 choose 3. This is the ways of no kings or no hearts. How many 52 card hands are there total? 52 3-card hands, or 3 cards, 3-card hands from a deck of 52. Thank you. So that means there are 52 choose 3 minus that number, and that's your answer. Yeah, don't simplify it further than that. That's totally okay. Nice. Cooper tab specifically, which one? Where we subtract this? It is similar. It is similar. It's not quite the same in the sense that you want to be careful about complements. Like you don't need to use complements in Namir for 2.1, but it is a similar sort of argumentation process. Yeah. Okay, so here, let me maybe draw a picture. So if I said, here's the set A and here's the set B, right? And I wanted you to tell me what the area of their union was. Well, in terms of the area of A and B, what would it be? So what is the area of A union B? Well, you'd say it's the area of A, right? Plus the area of B. That number's too big though, right? Do you all agree? A plus B is too big because I counted everything in here twice because that's in both A and in B. So I have to subtract the intersection. Yeah, okay, hold on. So yeah, Jack Namir confirms exactly 13 hearts and 3 kings. And it's 3 kings because you already accounted for the king of hearts in the hearts, right? Or you could say 4 kings and then subtract 12 hearts, where you only do 12 hearts because you've already done the king of hearts. So yeah, that's why it's 36. Can I use the way of rolling 2d6 to make this more obvious? I don't think so. in the sense that when you roll 2d6, you really have two different things, right? You have the first die and the second dice. And here we don't have two separate events, right? Like that's not, we don't have those things separately. So I can't like draw a table and say, how are these things related? Right? Like that's not, let me see if I can think of like a visual aid here. Let me, instead of calling these A and B, so this is no kings, right? This is no hearts. And then in the center here, we have no kings and no hearts, right? And the problem is that if I count the number of no kings, then I get this. If I count the number of no hearts, I get this. And you can see I've counted no kings and no hearts twice, right? So I have to get rid of one copy of no kings and no hearts to rebalance that out. For the assignment, is it fine if we just put NCN for our answers? Yeah, no, just leave it as N choose K. Like that's totally fine. If that's what you're asking. Yeah, I mean, like some things I think you should do in the sense that like if you ever find, okay, if you want to leave it as 5 choose 1, that's totally okay. But notice that if you're ever doing 5 choose 1, your answer is 5, right? But no, leave 36 choose 3 as 36 choose 3. Don't simplify that. And you're not going to lose marks if you leave it as 50 choose, like as 5 choose 1. If you leave it like that, that's totally fine as well. Like don't worry about it at all. It doesn't matter. Owen, yeah, I don't know what to tell you. I just was always on something. I would schedule it out. So Mondays I would do this class, Tuesdays I would do this class, Wednesdays I'd do this class, Thursdays I'd do this class, Friday I'd work, Saturday I'd work, Sunday I'd work. And that was basically how I did it. Will we lose marks if we simplify? No, but like keep in mind that your TAs are probably going to be looking for final answers like unsimplified. So at least give them the unsimplified and then simplify it. Like that's totally okay. But they're probably not looking for the raw number. So give it to them as something which you can see. No problem, Gerbertab. So the part in the center is for all kings and kings with 4 suits. Connie, I'm not quite sure what you mean. So like there's more than just like we're not just picking suits and ranks here, right? When I draw that picture of the intersecting yellow and blue sets, we're counting all the possible hands. So the yellow is all the hands that don't have any kings in them whatsoever, right? And the blue is all the hands that don't have any hearts in them whatsoever, right? So what we found is that this was 48 choose 3 and that the blue was 39 choose 3. Okay, but the problem is precisely this bad black thing I'm going to draw in here. That's not very, here, let's make it nice and thick. No, that's not thick at all. There we go. This thing got counted twice. Right? And that's bad. We only wanted to count it once. So we have to remove one, right? Like if I counted it twice, if I take another copy out, then I'll have fixed it, right? So that's what we're doing there is we're accounting for the fact that I counted that twice. See, Christian, more general question. Okay, Connie, sweet, awesome. That's what I like to hear. More general question, do we multiply when all conditions? Okay, Okay, this is an interesting question. So basically, I think I got a direct message which is asking basically when do we add and when do we multiply, right? And the important thing to remember is basically if you break it into cases, you're going to add your cases together, and you multiply once you've right. So the basic counting principle says, if you have 3 boxes, you look at the options for this. Let's say this is K, this is M, and this is N, right? And basic counting principle says that the total number of ways for doing this is, but you're saying now for probabilities. So you add, so the probability of, this is, if they're independent, yes, you multiply them. Maybe that's what you're asking. Okay. If you're taking a union, it's much harder. Okay. So if you're independent, you can multiply them. If they're not independent, you can't. If when you take the probability of the union, you can do exactly what we did above, right? That's exactly what this blue and yellow picture here is at the top. The probability of the intersection is the probability of the sum, or the probability of the union is the probability of the sums minus an extra intersection. If your events are mutually exclusive, then this part is 0 and you can just add, right? But generally, if they're not mutually exclusive, you do have to account for that. Yeah, and Jack, I guess you got it before I did. And then Kurdi, it depends, right? So Kurdi, keep in mind that in the assignment, you're doing a 7-card hand, not a 5-card hand, and that is actually going to change that number. Can we do at most? Yeah, we could, but so let me think. Like at most 2 hearts and 2 kings. Sure, I guess we can. So at most 2 hearts and 2 kings in a 5-card hand. I mean, this is going to be a nightmare. Yeah, I mean, Ariana, kind of the problem is that that's very ad hoc, right? Like in the sense that you kind of have to make that call depending on what the problem says. This one's really going to be nasty. So yeah, I mean, again, in this case, I would probably, oh man. Well, let me think about how we do it. Okay, so if we do it directly, then I think we've got 6 cases. No, we potentially have 9 cases. So we have to look at 0 hearts and 2 kings, 1 heart, 2 kings, 2 hearts, 2 kings, right? So we would have to look at these cases. So 0 hearts, 0 kings, 0 hearts, 1 king, 0 hearts, 2 kings, 1 heart, 0 kings, 1 heart, 1 king, 1 heart, 2 kings, and then 2 hearts, 0 kings, 2 hearts, 1 king, 2 hearts, 2 kings. So if we did it directly, we'd have to do those 9 cases, all of them separately, right? Now, if we do the complement, so the complement of this would be at least 3 hearts, or at least, and I think this is going to be easier, 3 kings, right? Now, at least 3 hearts, you would still need to do this by scratch because you're obviously not going to do this one, I think, by complement. So at least 3 hearts is going to be 3 hearts. And then you're going to add to that the case of 4 hearts. And then you're going to add to that the case of 5 hearts. Right? And then here you're going to do the same sort of thing. All right, so 3 kings plus 4 kings plus 5 kings. And then you have to worry about the king of hearts. So what you're going to have to do is with each of these cases, break it into 2 cases of whether the king of hearts is in there or not, right? So if I do I have to? I don't think there's a nice way of doing this problem. Like this is, and the numbers you chose are basically like maximal number of cases that we did. So at least 3 hearts or at least 3 kings. And then we'd have to subtract the number of things that have, yeah, okay. So what we could do is we could just add these, right? So then we would add these together. And then we would subtract the number of 5 card hands that have it both at least 3 kings and at least 3 hearts. And maybe that's not too bad because there's only so many ways that can happen, right? At least 3 kings and at least 3 hearts. And oh man. Okay, so what does that mean? It means that you basically need to have heart, heart, king of heart, king, king, right? That's the only way this case can happen. And so that's not bad because there's only one way of doing this. And then there's 13, choose 2 ways of doing this. And then, no, not 13, 12, because we got rid of the king of hearts. And then there's 3, choose 2 ways of doing this. So what you would do is you do this, add them together, this, add them all together, add the answers for both of these cases together and subtract this, and then take the complement of that, and that would be your answer. And that's faster, right? That is actually better than doing 9 cases, but you could do it that way. And Brandon, that is good advice. Yeah, that's a great advice. But yeah, you can see like this is a hard question. This is why we usually say at least 1 or at most, 4 or something like this. Like we're trying to set up questions where the complement is actually really small, right? But when you said at least or at most 2, that's actually like it and the complement are almost the same size. So we're pretty much screwed no matter what we do. It's like that perfect Goldilocks zone of neither of them being particularly easy to compute. Right? So that's definitely a messy one for sure. But it's a good, if you really want to challenge yourself before a test and you want to see if you can do it, that's a good one. Okay, any other questions? Right, so Kurdi, why isn't it 13 in a standard deck? Think about a standard deck and 5 cards. Why isn't the answer 13? Why is the answer 10? Right, I'm glad, Ariana. And Kurdi, exactly, right? Okay, now what if I give you a standard deck still and give you a 7 card hand? Is it still 10? Like, how would you start the straight? How many options do you have? So you're saying it's still 10? Can you start a 7 card straight with a jack? Right. Can you start it with a 10? Okay, so let's pretend we started with a 10. 10, Jack, Queen, King, Ace. I gotta have 7 cards. What's the last card? Because the ace has to finish it, right? Oh, and yeah, that seems reasonable. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it can't make a circle, right? The ace can't occur in the middle. The ace has to be the end or the beginning, but it can't occur in the end. So we can't start in a 7-card hand in the standard deck. We can't start with a 10. And for the same reason, we can't start with a 9. Can we start with a 9? 9, 10, Jack, Queen, King, Ace. Wait, what did I miss up here? 9, 10. No, 10, Jack, Queen, King, Ace. 9, 10. I am tripping hard. Oh yeah, there's 2 cards missing here, right? And then here there's only 1 card missing, but I still can't start with a 9. So Kurdi, it's not 9 because you can't start with a 9 either. Brandon, maybe yes, maybe no, I can't really say, but that seems reasonable. And Jack, yes, you can end with an ace. Oh, for the extended deck, I can't confirm that because it is an answer to like a question, right? But I think you can reason it out because there's only finitely many options and it's probably related. So, at some point you have to trust that you understand what's going on. I wonder if this is legitimately like yeah, does it not say that though in the assignment, Jack? I feel like we explicitly wrote that in, didn't we? Yeah, so Jack, it says a straight occurs when the 7 cards have consecutive ranks. Note that the ace can be used to finish a straight, for example. Yeah. It's like, I just go back and fix it. It shouldn't make a big difference. Like, you're just going to have to change a number here or there, right? But just figure out where did you assume that it couldn't. It's just going to, you're basically going to add 1 to a number, and then you just have to make sure you follow that number through and you make the change, and it's not the end of the world. Kurdi, yeah, sure. And that gives you your answer then, right? Perfect. And Jack, yeah, I don't think it'll be that much work to fix, right? Same thing, even when we were doing the postal codes, I realized afterwards I made a mistake and had to go back and fix it, but I changed like a 10 to an 11, and then basically it only changed the final answer because you kind of count those cases separately, right? I don't think it'll be a big deal. And I think there's only one question where we ask about the straight, right? So you don't have to redo the whole assignment. You just got to tweak that one question. You'll be okay. It's not the end of the world. No problem, Tudor. See you later. This is an interesting thing to me. I wonder, like, so many of you are having, like, have never, I guess, played with cards extensively. And I don't want to sound like an old man. Yeah, exactly. It doesn't affect question 2. I don't want to sound like an old man, but like, when I was young, we used to do this in high school because, we didn't have like smartphones and stuff. And all of our Tamagotchis got taken away, and we weren't allowed to like, do Pokemon cards because those were banned. So like we had to just play with cards, and a lot of us would play cards during high school, like during breaks. And I wonder if that's not true anymore because everybody's got phones, right? Again, I'm not trying to sound like a cantankerous old man, but like, and that's what I'm saying, right? Like we all played a ton of cards and a bunch of like silly games that we made up, and we would make up card games and do stuff like this. Yeah, but it probably wasn't as like, we did it out of boredom, right? I imagine people, maybe for you guys in high school, were just like, hey guys, let's play a card game. And it wasn't so much as out of boredom as of maybe interest. I don't know. Okay, that's interesting, right? So like, but that doesn't seem to be a universal thing. Nice, Owen. Very nice. Very nice. I thankfully never got into that, but there are two people in our department who are huge Magic the Gathering people. So much so that they are like mods on most of the Reddit forums for Magic the Gathering, which I don't understand because I don't know, there's something like Legacy or something. I don't know. So they're the mods on it. They've both written like papers on Magic the Gathering. They both tend to do pretty well in tournaments. Like it's legitimately a side hustle for them. And I don't know, it's crazy. It's a next level for them. And they talk about, like being a strong mathematically, I guess, is useful in some way, but I don't know enough of it. Oh, there's some crickets there, Jack. I guess not. Okay, everyone, though, I'm going to take off. If you guys want me to leave the meeting open so you guys can, mess around, I'm happy to do that if you want, but otherwise I'm going to take off now. I've got a couple of stuff I got to do. Yeah, that's right. Yeah. You can play some cards, find some way of, find a website that does it, right? Like there actually are tons of really, really good websites where you can just jump in and play cards with someone. No problem. Thank you, Ariana. All right, everyone, I'm going to take off. Have a good night. Have a good weekend. I'll post something on Friday about your term test. Otherwise, work hard and try and relax a bit this weekend, and I'll see you next week. Ciao.